What you're listening to is the opening of Camille Saint-Saëns's Danse Macabre, which uses an interval of musical notes that sounds so dissonant that people in the 18th century called it the Diabolus in Musica, the devil in music. It sounds like this. But why exactly does this interval sound so dissonant? To answer this question, we have to delve deeper into the concept of pitch. Scientifically, sound is just particles pushing against one another to create waves of vibration. Pitch is based on the number of vibrations per second. This is the graph of a sound wave. The segment from one peak to the next is called a cycle. The number of cycles that reach your ear in 1 second is called the frequency, measured in hertz, and as the frequency increases, so does the pitch. Most instruments use either strings or air vibrating in pipes to produce sound. Shorter strings have higher frequencies and therefore higher pitches. You can hear this on a viola compared to a cello. This also works for wind instruments. Shorter pipes have higher pitches, like a piccolo compared to a tuba. When you play a note on a piano, a little hammer inside hits a string that vibrates at a certain frequency. For this note, middle C, that frequency is about 262 Hz. If you multiply this frequency by 2, you get the same note 1 octave higher. If you multiply it by 3, you get this note, G, and if you multiply it by 5, you get this note, E. This set of intervals that we get from multiplying the original frequency by whole numbers is called the harmonic series. Dividing a frequency by 2 gives you the same note an octave lower. Using this, we can move the notes of the harmonic series to the same octave to produce this beautiful C major chord. In fact, all the intervals of the major scale can be created with these ratios. Let's see how this plays out on a guitar. I'm going to take the note D and play a perfect fifth, which is A. Now if I measure the vibrating length for the note D, I get about 27 inches. And if I do the same for the note A, I get about 18 inches. So, if you do the math and you divide 27 by 18, you should get the ratio for a perfect fifth, 3:2. Now remember that devil's interval from earlier? The reason why it sounds so dissonant is because the ratio of frequencies is 64:45. Compared to the 5:4 ratio of a major third, this interval is a lot more complex, and complexity adds tension. This combination of tension and resolution is what makes the music we listen to every day. So the next time you're listening to music, maybe you'll appreciate the math behind it as well.